Okay, let's wait a couple minutes and then we start. Okay.
So, Rogerio, how did your lectures go?
I think they went okay. Can't complain.
Have you lectured on this topic before?
Yes. Yes. So I lectured. There's a series of CERN Latin American schools. So that's where I taught this for. Of course, I put new things because otherwise it gets too boring for me.
It was actually interesting preparing these lectures because, if you remember, I taught some number of years ago, maybe 7 years ago, I think.
Yeah, in one of our schools.
And again, I think it was on BSM, so it was kind of curious. And I had my old lecture notes, and I went back and looked what's changed, in 7 years, And what I realized that those lectures were a lot more about supersymmetry.
I remember those lectures, but I remember he talked a lot about shift symmetry and axions, and if I remember correctly.
Yeah. So I think it was about a lot of it was about supersymmetry and also about little Higgs theories.
Little Higgs.
Yeah. So some of that is still there, not so much supersymmetry, but the shift symmetries, but now in the form of hidden in the composite Higgs.
Yes.
Part of the story.
That's right. Very good. Okay, maybe we should start. Okay, so hello everyone. So we're going to start the last lecture of the day. So it's the first series of lectures. But before starting, you probably noticed in the program that this particular set of lectures is called the Pontón Memorial Lectures. So I want to talk a little bit about Eduardo Pontón, who gave the name to this series of lectures. So Eduardo Pontón, and he was a brilliant theoretical physicist, working mostly in particle physics, originally from Colombia. And he did his PhD at the University of Maryland, and then postdocs at Yale Fermilab for having a professorship at Columbia University. And in 2013, Eduardo joined. He was the first hire of the then recently created ICTP South American Institute for Fundamental Research, and he passed away June last year. It was really untimely, unfortunately. He was an amazing person. And this school is actually the brainchild of Eduardo. So I think it's really well deserved. So this is our first Eduardo Pontón Memorial lectures. And I think there's no one more appropriate to give these lectures than Professor Zackaria Chacko. So let me say a few words about Professor Chacko. So Professor Chacko, he did his bachelor in science and master in science at the Indian Institute of Technology in Kharagpur. Please correct me if my pronunciation is not proper. And he did his PhD at the University of Maryland. So he was a classmate of Eduardo. And after that, he was a postdoc at the University of Washington in Seattle, also a postdoc at the University of California, Berkeley, assistant professor at the University of Arizona, and then he joined University of Madison in 2007, and is an associate professor there. And Professor Chacko is an expert in physics beyond the standard model, and he's going to give this set of lectures. Again, it's the first Pontón Memorial lectures on new physics beyond the standard model. So Chacko, please.
So I'd like to thank the organizers for inviting me to give these lectures. So I'm talking about new physics beyond the standard model, which was actually the topic closest to Eduardo Pontón's heart. So I feel quite honored to give these lectures. So this first, I hope you can all see my screen. So this first page is an outline of what I hope to cover in these lectures. So so I'll begin with a discussion of why we need physics beyond the standard model. Then I'll discuss constraints on new physics. What are the things you need to think about when you're constructing models of new physics? And then I'll discuss the hierarchy problem and some of the solutions that have been put forward to address it. So I'll discuss supersymmetry, composite Higgs models, and some more recent work on neutral naturalness. And then I hope to discuss the axion solution to the strong CP problem. So so beyond the standard model, physics is a vast topic, right? So my approach has been, my approach in these lectures is to focus on a few specific things rather than to touch on a whole bunch of things, right? But hopefully in the topics I cover, by the end of the lectures, you will be, up to speed, almost pretty much at the level of current research, or very close. That's my hope.
Oh, Chacko, I don't know if it helps if you put in full screen mode, if it's any better than.
Let me see. Oh, I see. Hold on.
No, it's the in the view.
In the view.
It doesn't. No.
Hold on.
Okay, doesn't matter. Doesn't matter. Not actually, it's not better. Sorry.
Okay.
sorry for this wrong suggestion. Sorry.
Okay, it's maybe I can make it a little bit bigger. Hopefully that helps a little.
Yeah, that's fine. That's fine. Thanks.
Okay, so the first question is why do we need physics beyond the standard model? As you know, the standard model does an outstanding job of explaining most experimental data. In fact, almost all experimental data. But nevertheless, we now have conclusive evidence that there must be physics beyond the standard model. So let me explain what that is. So the first point is that over the last 20 years or so, it's become clear that that the neutrinos have mass and that they mix with each other, right? And in the standard model, there's no, given the particle content and the gauge quantum numbers of the particles, there's no way you can write a mass term for the neutrinos at the renormalizable level. And so that means that there must be physics beyond the standard model to explain neutrino masses, right? The standard model does not explain why there is more matter than antimatter in the universe. So we are all made up of baryons, right? And so there's an open question. Why are there more? Why is there an excess of baryons over antibaryons, right? And there's no explanation for that within the standard model. Now, so here again, in the last 2-3 decades, it's become increasingly clear that about 80% of the matter in the universe is some form of dark matter, something which is not baryonic and non-luminous. And there is no particle in the standard model that can play this role. So when I was a student, it was still possible, maybe for the neutrinos to play the role of dark matter, right? But now, given the current bounds on neutrino masses and the improvements in cosmological measurements, that's simply not viable anymore. So there must be some particle outside the standard model which is playing the role of dark matter. So once again, a compelling reason for physics beyond the standard model. And so the standard model does not explain the apparently acausal density perturbations that seeded the growth of structure in the early universe. So what does this mean? So the point is there's structure in the universe. The matter in the universe has clumped into galaxies and clusters of galaxies and even larger and smaller scales. And these structures grew out of primordial density perturbations in the early universe. Now, there's a remarkable fact, which is that there appear to be correlations in structure across distances which were apparently never in causal contact, right? If you just trace the Big Bang back to the beginning of time, it appears that you end up with a problem because there are correlations in structure between points which were never causally connected, right? And that's if you follow the standard Big Bang evolution that you would get from the standard model alone. And so you need some mechanism to explain that, and it cannot be explained within the standard model. So, so you can see there's 3 or 4 very compelling observation-based reasons to believe that there is a physics beyond the standard model. So apart from these experimental observations, there are some more theoretical reasons for us to expect physics beyond the standard model. The first is the fact that gravity is not a renormalizable theory, right? Gravitational interactions are Planck suppressed, right? And what that means is that we don't have, the standard model simply cannot describe physics at energies above the Planck scale. So if you have momentum transfers at energies above the Planck scale, that's the scale where gravity becomes strong, right? And standard models simply cannot describe such processes, right? It simply becomes non-calculable. So the standard model cannot explain the large hierarchy between the value of the cosmological constant, right? So the cosmological constant we know from observations seems to be about 10 raised to minus 3 eV raised to 4 powers. And this is much, much smaller than other scales in physics, such as the QCD scale, which is about a GeV, and the electroweak scale, which is about 100 GeV. And the reason this is a serious problem is that because of quantum effects, these higher scales feed into the cosmological constant. So you would naively expect the cosmological constant to be at least as big as the electroweak scale. And that happens because we live in a quantum universe, and so there are radiative corrections to the value of the cosmological constant. And since these higher scales, we know these higher scales are there in physics, they should feed into the value of the cosmological constant. And we would expect the cosmological constant to be about at least electroweak scale. And that's, assuming, that's making a very, very conservative assumption that there are no scales above the electroweak scale. If there are scales above the electroweak scale, the value of the cosmological constant would be even higher. But even if you just take it that the cosmological constant should receive correction from the electroweak scale, we are left with a fine-tuning problem of more than 50 orders of magnitude. Okay? So the cosmological constant is more than 50 orders of magnitude smaller than we would expect. And that means there has to be some delicate cancellation between the bare value of the cosmological constant and these quantum corrections. And that's a fine-tuning problem. Now, one proposal which has been put forward to explain this is anthropics. So the idea is that the cosmological constant governs how quickly the universe is expanding. If the cosmological constant was very large, the universe would expand so quickly that structure would never form, and then we wouldn't exist. And so we wouldn't be here to complain about the cosmological constant problem. Okay? And so that's one of the explanations which has been, put forward, right? And put like that is difficult to, is that a sensible explanation or not? But it can be given a little bit more teeth in theories where you have a multiverse. So you have many, in theories where you have many, vacua. You could have different parts of the universe where where the vacua are different. You have different gauge groups and things like that. And if the universe is composed of these many different parts with different fundamental constants and different cosmological constants, for example, if you have a multiverse with enough different regions like that, for example, if you have a multiverse with more than 10 raised to 50 different regions, you could imagine that we are living in the one where the cosmological constant is small, because that's the only one where life could exist, right? A little bit like we live on the Earth rather than on Jupiter, because even though the Earth is a lot smaller than Jupiter, the conditions on Jupiter are not hospitable to life. Right? So yeah, so that, so that's one of the possible explanations, right? The standard model cannot explain the large hierarchy between the electroweak scale, which is of order 100 GeV, and the Planck scale, which is of order 10 raised to 18 or 19 GeV. So the Planck scale is where quantum gravity becomes important. And in fact, the standard model cannot explain the hierarchy between the electroweak scale and any other scale that's larger and which might exist, such as if grand unification happens, or you have a theory of inflation to explain the primordial density fluctuations. Those would all be higher scales. And once again, quantum corrections from these higher scales would feed into the electroweak scale. And you would expect the electroweak scale to be a lot larger. And we would be left with a, and the only way to have such a small electroweak scale is there's a tuning between much larger parameters, and the tuning would be at the level of, assuming the high scale is the Planck scale, at the level of 1 part in 10 raised to 30. So once again, this is this may have an anthropic explanation. If the Higgs mass was much larger, the electroweak scale would be much larger. The electron mass would be different. Chemistry wouldn't work. Who knows if life is possible, right? So, once again, there could be an anthropic explanation for why the weak scale is what it is, right? But, there are other possible explanations, right? And it's definitely something that that needs to be thought about. So in the standard model, we don't understand why the electric dipole moment of the neutron is so small. This is called the strong CP problem. So, so naively, we would expect the neutron to have a electric dipole moment, which is about 10 orders of magnitude larger than what we see as the observed upper bound. And this problem is similar in some sense to the cosmological constant problem and the hierarchy problem. But one important difference is that in this particular case, there's no known anthropic explanation. The electric dipole moment of the neutron could be quite a lot bigger without really, changing life as we know it. Right? So so in that sense, this problem is a little bit different from the two problems I talked about. So so I've distinguished, so in the discussion so far, I've been distinguishing between problems that that require new physics based on hard observational facts, and these three, which are or rather these four, which which correspond to peculiar, the fact that the standard model is a consistent theory that explains the data, but the values of the parameters are very peculiar and need to be chosen in some very peculiar way in order to fit the data. Okay. So these four reasons for physics in the standard model that I just discussed are different from the first four, in the sense that when it comes to the first four, in each of them there's a hard experimental fact that cannot be explained by the standard model as we know it. The four I've just discussed, they can't. There are parameters in the standard model that explain all the data. It's just that the choices of parameters that you have to make are somewhat peculiar and have to be chosen rather in a way that seems to require an explanation. So then, apart from this, there are some other features of the standard model that seem to scream out for an explanation. So if you look at the pattern of quark and lepton masses in the standard model, they seem to exhibit a hierarchical structure. And so although the fermion masses are radiatively stable, the quantum corrections to their values are small, this seems to hint that there's some underlying structure that determines this pattern. And we don't know what that is. And apart from that, there's also the fact that electric charge is quantized in the standard model, right? And that there's no explanation for that. So in principle, the only constraint on the values of hypercharge in the standard model are coming from anomaly cancellation. But that would still, but that doesn't necessarily force the charges to be quantized. So the fact that all the electric charges in the standard model are integer multiples of 1/3 seems to indicate that there's some underlying structure that warrants explanation. Okay? So these, I think, are the most compelling reasons to think that there's physics beyond the standard model. So any questions so far?
There is one question by Ganesh. He's asking if Randall-Sundrum models solve these hierarchy problems, and what are the problems with Randall-Sundrum model. So I think we're going to talk about this later.
Yeah, so Randall-Sundrum models are one proposed solution to the hierarchy problem between the Planck and weak scales. They're an interesting class of models. I won't go into this in detail in this, because there is a duality between Randall-Sundrum models and composite Higgs models. Okay? So Randall-Sundrum models that solve the hierarchy problem are dual by the ADS-CFT correspondence to composite Higgs models, which we will talk quite a little bit about. So we will come back to this at some point.
Okay, there's another question by Nihal Mittal. He's asking, if you can explain again why other scales should feed into the cosmological constant.
So the cosmological constant sources gravity. Okay? And unfortunately, I don't have a way to write here, but roughly speaking, what's going on is that by saying the cosmological constant sources gravity, what I mean is that you can draw a line with a graviton coming in, and the graviton is being sourced by the value of the cosmological constant. Now, you can draw a graviton line coming in, and for example, draw a loop of quarks, okay, or something like that. That is sourcing the graviton, okay, and so then if you calculate that loop of quarks, right, you'll see that that in principle it could be infinite or anything, but there are even finite pieces coming from that, and those finite pieces are of order the QCD scale, for example, right, or or the electroweak scale, all right. So what will happen is that if you draw a diagram with just one graviton coming out, and the graviton is coupled to a loop of quarks or a loop of some other particles that are in the standard model, what you'll see is that that diagram is non-vanishing, and you will get it could correspond to a source for the graviton whose value is of order the scales in the problem, like the QCD scale or something like that. On the other hand, we know that because the cosmological constant is so small, we know that the graviton is not being sourced that much. So there must be some big cancellation between this loop contribution and the tree level, the bare value of the cosmological constant.
Okay, and the last question now is from Sudipta. She's asking why neutron has finite electric dipole moment.
It's big. It's so roughly speaking it's the thing that sources the neutron electric dipole moment is actually an angle. So it only runs between 0 and 2 pi. And so it's kind of funny. The radiative corrections can be infinite, but then you have to divide by, you have to mod out by 2 pi. So in the end, it's always something finite. Okay, so what you observe will always be finite. We'll actually see a little bit.
Okay, there are no further questions, Chuck. We can move on.
All right. Okay, so let's talk a little bit about theories of beyond the standard model. So, so let's look at the space of all theories of beyond the standard model, right? So, so of course that's vast, right? All possible extensions of the standard model. Now, within that, there's a subset of theories that address a known problem of the standard model, right? For example, the problems I just discussed. And then there's a subset of all beyond the standard model theories that are experimentally testable, right? And we are most interested in theories that live in this overlap region. It's completely possible to write down a theory that addresses a problem of the standard model and is actually interesting and compelling, but which is not testable, at least not testable anytime soon. And of course, there are lots of theories that are experimentally testable, but which don't seem to address any problem of the standard model, right? So, but most of our focus when we work on beyond the standard model physics is in looking carefully at this region, which this overlap region. Okay, so the gold standard in beyond the standard model physics is to find a new theory that addresses some problem of the standard model, and which can be tested in some completely new way, right? So that's like the gold standard. Of course, it doesn't happen very often, right? Beyond the standard model is an old subject, and but it does happen occasionally. Yeah, so so some examples of very well motivated theories that are not testable are, for example, the high scale seesaw model for neutrino masses. So that's one of the probably the most compelling explanations for neutrino masses, but yeah. And within that, you can within the seesaw model, you can also, in principle, explain the origin of the baryon asymmetry, the matter-antimatter asymmetry in the universe. Okay? But it's probably not testable ever, right? And and many models that explain the matter-antimatter asymmetry are compelling, but they're very hard to test. So it's just an unfortunate fact that that this overlap region is not as large as we would like it to be. Okay? That's just the reality. But nevertheless, most of our focus, and definitely most of my focus in these lectures, is going to be on theories that live here. Now, historically, a lot of attention has been paid to models that address the hierarchy between the Planck and electroweak scales. And that's because those theories live in that shaded region. Those theories are, address a problem of the standard model, and they're usually testable. So that's one reason why historically a lot of attention has been paid to this particular class of theories. Okay? And that's going to be the case in these lectures as well. All right. Now let's turn to constraints on new physics. So for a model of new physics to be viable, right, it needs to be consistent with every single experimental fact known to mankind. Okay, if there's a single well-established experimental fact that it cannot explain, that theory is wrong. Okay, no matter how beautiful it is wrong. Okay, and the thing is, there's just a lot of experimental facts. The range of experimental facts is just incredible. Okay? So there are limits from direct searches for new particles, and also indirect bounds from new physics contributions to rates for various processes. Okay? So it ranges all the way from colliders to the cooling rates for stars, to the abundance of helium in the universe, to details of the CMB, right? The range of constraints is truly vast, right? And when you write on a model of new physics, it's one of the hardest things to do is to be sure that it's actually consistent with all these facts. Okay? So if the model is related in some way or a cousin of some existing model, usually you can use that, you can leverage that to figure out whether it's consistent or not. But if you're writing down a model which is radically different from anything that's been written down before, it can be really hard to know whether it's consistent or not, right? And even the best and most experienced model builders screw up occasionally, okay? And that's fine, okay? That's part of that goes with the game, okay? No risk, no reward, okay? That's that's the way it is, right? At least in this business, okay? So I certainly cannot discuss, the full range of constraints in physics we understand. Well, that's just impossible, right? So I want to focus on some characteristic features of the standard model that, once you extend the standard model, are often not present. Okay. So these characteristic features that I'm going to discuss now there's four of them. There's accidental baryon and lepton number symmetries, suppression of CP violation, suppression of flavor-changing neutral currents, and custodial Su symmetry. Okay? These are four properties of the standard model that very often are not properties of extensions of the standard model. Okay? And so these are a good place to look for new physics. Okay? And they can be, and since these are properties of the standard model, they often put some of the most powerful constraints on models in new physics, right? So what I'm going to do now is I'm going to consider these four features of the standard model in turn, right? Because some of them will show up down the road once we start considering specific extensions of the standard model. Okay, so let's start with the simplest one. Let's talk about accidental symmetries of the standard model. So, okay, so baryon number is an accidental symmetry of the standard model. So what does that mean? What it means is that, suppose I give you the particle content and the gauge symmetries of the standard model. Okay, it is not possible to write a renormalizable term that violates baryon number. You just can't. Just write down all the possible terms that are allowed by symmetries. And you'll find that at the renormalizable level, you won't be able to find an operator that violates baryon number. Okay? So that's what we mean by an accidental symmetry. You don't impose it as a symmetry, just that the fact that you can't write down an operator at the renormalizable level means that any baryon number violating effect is suppressed by some high scale, and so you expect it to be suppressed. So this is also true of lepton number in the standard model. You won't be able to write any renormalizable operator with the standard model fields that violates lepton number. But in this case, in the case of lepton number, it's even more powerful, because in the standard model, electron number, muon number, and tau number are all separately conserved as accidental symmetries. So so there is 3 accidental symmetries in the lepton sector, okay, corresponding to each flavor of lepton. And the overall lepton number is the diagonal subgroup of these 3 individual lepton numbers. Now, non-perturbative effects in the standard model violate these global symmetries. Okay? And it turns out that the only true global symmetry is a U1 of B minus L, baryon number minus lepton number. That's the only symmetry which is preserved once you turn on non-perturbative effects. But these non-perturbative effects are usually only important in the early universe, okay, at high temperature. At 0 temperature, where we effectively live now, all non-perturbative effects are exponentially suppressed, okay? And so they can usually be neglected. All right. So for all practical purposes, okay, at 0 temperature, baryon number and your 3 lepton flavor numbers, right, muon number, electron number, and tau number are all effectively conserved. Now the point is that these accidental symmetries in general are not symmetries once you go into extensions of the standard model. So so the bounds on processes that violate these accidental symmetries, okay, so for example, proton decay would violate baryon number, and mu to E gamma would violate muon number and electron number. Okay? So the bounds on processes like this are often the most powerful constraints from extensions of the standard model. And yeah, so that's something to keep in mind, right? If you're writing down a model of new physics and you're violating these accidental symmetries of the standard model, you've got to be careful, okay? Those things are pretty well measured. Okay. So let me stop here and ask if there are any questions.
I don't see any questions in the chat at the moment. Give you 30 seconds if you want to write something in the chat, or you can also raise their hands and ask. Okay, Chacko, I don't see any questions at this point.
Good, let me go ahead. So the next thing I want to talk about is suppression of CP violation. Okay. So in the standard model, there's only one source of CP violation, which is the phase in the CKM matrix. So let me remind you what the CKM matrix is. The CKM matrix is the matrix that captures the flavor structure in the couplings of quarks to the W bosons, right? So the way this happens is that you start out with the Lagrangian for the standard model, right? And say in the flavor basis, And once the Higgs gets when the Higgs gets a web, the quarks get masses. And now when you rotate to the mass basis, right? Rotate from the flavor basis to the mass basis. What happens is that the flavor structure now goes into the couplings of the quarks to the W boson. Okay? So that flavor structure is now encoded in this matrix, which connects the quarks to the W boson. And this matrix is the CKM matrix. Okay? And if you're wondering about this factor of √2, it's because W plus minus have a factor of √2 relative to W1 to 3. Okay? Okay. Here, alpha and beta are flavor indices. Now, okay. So remember that the CKM matrix has it has a bunch of entries, but it has only 4 physical parameters. So there are 3 mixing angles and 1 phase. Okay, and that 1 phase is the source of the CP violation, the standard model. Okay. Now, in the standard parametrization of the CKM, okay, this is what it looks like. It's some fairly messy beast. Okay, but there's many ways to parameterize the CKM. Okay, this is just one of many parameterizations. But the point is that there are 3 angles: theta 1, 2, theta 1, 3, and theta 2, 3, and delta is the phase. Okay, this is how they appear in this parametrization of the CKM. So in this parametrization, from the data, sine theta 1, 2 is 0.22. That's like the Cabibbo angle. And then sine theta 2, 3 is 0.04. So that's pretty small. And then sine theta 1, 3 is really small. It's 0.004. On the other hand, the angle, the phase, right, is big. It's 66 degrees, right? So the CKM phase is actually pretty big, all right? Now, the fact I want to stress here, okay, the kind of crucial fact that I want to point out is that CP violation vanishes in the limit that any of the 3 mixing angles vanishes. So if any of these 3 angles was 0, CP violation would vanish in the standard model. Okay. And that's really important because these angles are small. In fact, one of them is very small. Okay. So, and so the phase is large, but the mixing angles are small, right? Especially this one. And for this reason, CP violation is suppressed in the standard model. Okay? It's not suppressed because this phase is small, because the phase is actually big. It's suppressed because these mixing angles are small. Okay? And for that reason, okay, CP violation in the standard model is suppressed. So if you have new physics that contributes to CP violation, you have some extension of the standard model that contributes to CP violation, that's very constrained. Okay, because you're fighting, you're fighting against the product of all these mixing angles. Okay, so keep that in mind, right? So very small CP violation is a feature of the standard model. In general, not a feature once you go beyond the standard model, right? Okay, let me move on. Let's go to the next feature of the standard model: suppression of flavor changing neutral currents. All right, so let's say one day you open your particle data book. Okay. Nowadays, they used to give out the particle data book to they used to mail it out to every practicing particle physicist. But at some point there was some budget cutting, and now they don't mail it out anymore. I don't even know if they print it out. You can only find it online, right? But it used to be that owning the particle data book was your passport that you were a particle physicist. If you didn't have a particle data book, you weren't a real particle physicist. Yeah, you might be a string theorist, but you weren't a real particle physicist. Okay, so let's say you open the particle data book, right, and you start looking at some start looking at some decays, and you'll notice there's some pretty peculiar patterns there. For example, consider this decay. The branching ratio for the charge kaon to go to mu plus mu, okay, charge kaon to muon plus neutrino, is more than 60%. On the other hand, the branching ratio for k long to go to mu plus mu minus is at the level of 10 raised to minus 8. So there's 8 orders of magnitude between these two. And you think about you look at it naively, well, what's the difference? I mean, the only difference is that here an up quark has become a down quark. Okay, and to conserve charge, this neutrino has become a muon. Apart from that, what's the difference? Why should this be order 1 and that be 10 raised to minus 8? Okay, but open your particle data book, you'll see it's true. Okay, all right. So, you look at it, in both cases, the initial state is hadronic. The final state is fully leptonic. In each case, the decay violates quark flavor symmetries. Big deal. But the rate for one is suppressed with respect to the other by 8 orders of magnitude. Okay, that can't be a random coincidence. It's got to be something going on, right? So here's the crucial difference. In the first case, there is a net flow of electric charge into the leptons. Okay? So there's a flow of electric charge into the leptons. Okay? So that's a charged current process. We call that a charged current process, right? On the other hand, in this case, there is no flow of electric charge to the leptons. Okay? So that's a neutral current process. Okay? And in the standard model, flavor changing neutral current processes are very, very suppressed. Okay? And to show you that I'm just not making this up, okay, grab your PDG and look at this decay. Okay? Here's a B meson going to D naught L nu bar. Okay? It's not a very common decay, but it happens about 2% of the time. But here's another decay of the B minus. Okay, and this one has even more phase space because the K is a lot lighter than D. Okay, you can go to K star L plus L minus. And there's about 4 orders of magnitude, 4 or 5 orders of magnitude between these two. Okay. And once again, you can see in this case, there's a net flow of electric charge into the leptons here. Okay, so it's a charge current process. Here, there's no flow of electric charge into the leptons. It's a neutral current process. And this process, well, these processes violate flavor. So this is a flavor changing charge process, no suppression. Flavor changing neutral process, okay, suppression. Okay. Right. And so let me give you one more example, okay, to show you that the suppression only applies to flavor violating decays. So here's another thing you can find in the particle data book. Look at the decay of J psi. J psi is CC bar, charm, anti-charm. Look at the decay of that into mu plus mu minus. So this is clearly a neutral current. There's no charge flowing into the muons. Okay? But this is a pretty reasonable branching ratio. Okay? And there's no suppression here because this is not flavor changing. Okay? CC bar has no flavor. Okay? And so there's no suppression. So what you're seeing is that in the standard model, flavor changing neutral currents are suppressed. Okay? And that's a characteristic feature of the standard model. And now I want to go into that in a little bit more detail. Okay. So flavor change neutral currents in the standard model are doubly suppressed. They're not singly suppressed, they're doubly suppressed. And this, okay. So first of all, there are no tree-level flavor-changing neutral currents in the standard model. Okay. A tree-level flavor-changing neutral currents in the standard model is exactly 0, right? Now, there are flavor-changing neutral currents at loop level, but they're actually suppressed by what's called the Jim mechanism, and also by the structure of the Secant matrix. So I'm going to go into this in a little bit of detail. I'll first show you that there is no tree-level flavor-changing neutral currents in the standard model. Okay, I'll show you that. And then I'll show you that even though there are flavor-changing neutral currents at loop level, they're suppressed. Okay, so that's what I'm going to show you now. All right, so let's start at tree level. Okay. So what are the particles in the standard model that can mediate neutral currents? Okay, you have the photon, that's neutral, the gluon, the Higgs, and the Z. Okay. Now, just on line 1, you can say the photon and the gluon cannot mediate flavor change because those gauge symmetries are unbroken. And so the gauge kinetic terms of the fermions are always flavor diagonal. Okay. So the photon always couples flavor diagonally, the gluon always couples flavor diagonally, and that's guaranteed by gauge invariance. Okay. Because the gauge coupling comes with the kinetic term. All right. The Higgs is a little bit more complicated. The couplings of the Higgs are always diagonal in the mass basis. Okay? So the way to think about that is, so here's a Yukawa coupling of the Higgs to some quarks. The Higgs gets a web and the quarks get mass. So you expand out the Higgs like this, okay, say in unitary gauge. And you can see that the Higgs is appearing like V plus H, right? And so now once you go to a basis in which the mass is of the quarks is diagonal, so this Y is being diagonalized, because the Higgs is coming in this combination V plus H, the couplings of the Higgs are also being diagonalized, okay? So the couplings of the Higgs are being diagonalized, automatically once you diagonalize the couplings of once you diagonalize the masses of the quarks. Okay? So in the mass basis, the couplings of the Higgs are diagonal, right? And that's just because the Higgs is the particle that gives the quarks and leptons their masses. Okay? Okay. So one important fact to keep in mind, this is only true because we had just one Higgs doublet. Okay. If you have more than one Higgs doublet, so you have two Higgses that are giving masses to the quarks or leptons, then all bets are off. Okay. In general, you're going to get flavor changing neutral currents unless you choose some very, very special flavor structure for the couplings of the Higgs. So for example, that's what happens in supersymmetry. In supersymmetry, you have two Higgs fields, but one of them gives mass to the up-type quarks, and the other gives mass to the down-type quarks and leptons. And because one of the Higgses never talks to the down-type quarks and the other never talks to the up-type quarks, you don't get any flavor-changing neutral currents. But you need some special structure. If you have in theories with more than one Higgs doublet, you need some special structure. Otherwise, you'll always have flavor-changing neutral currents. But if you have just one Higgs doublet, like in the standard model, you're guaranteed that the couplings of the Higgs are going to be diagonal. Okay, in the mass basis, flavor diagonal in the mass basis. Okay. And because of that, the Higgs does not mediate flavor changing neutral currents in the standard model. All right, so we are done with the photon and gluon. We are done with the Higgs. Let's turn our attention to the Z. Okay, so the Z does not mediate flavor changing neutral currents. And the reason for that is that it couples to fermions of the different generations in exactly the same way. Right. For example, consider the couplings of the Z to up-type quarks. So let's say you start in the the flavor basis, right? So the couplings of the Z to the up-type quarks, to the left-handed quarks, you have half minus 2/3 sine squared theta W. Notice that's independent of the flavor of the quark. Okay, it doesn't matter whether you're talking about first family, second family, or third family. Okay. This coupling is always the same. And similarly, the coupling to the right-handed quarks, minus 2/3 sine squared theta W, is again completely independent of whether you're talking about the first family or not. Okay. So here, this alpha is a flavor index, but the couplings of the Z are proportional to the identity, okay, in flavor space. Okay. So that means when you rotate from here to the mass basis, the fact that the couplings of the Z are proportional to the identity in flavor space means that the couplings that once you're in the mass basis, the couplings of the Z are still going to be proportional to the identity. Think about it, okay? But you can convince yourselves that this is true. That since the couplings of the Z are proportional to the identity in the flavor basis in which you begin, and now you start rotating to the mass basis, the identity just doesn't. The fact that it's, you start with the identity means that this doesn't change. So the couplings of the Z continue to remain flavor diagonal in the mass basis. Okay. So what we have now shown is that at tree level in the standard model, there are no sources of flavor changing neutral currents. And more generally, once you're in the mass basis, the only source of flavor violation in the standard model is the Secant matrix. Okay, so that means that if you have tree level flavor violation, it had better involve a W boson, okay? And it had better, and that means you're dealing with a charge current. Okay, so now let's move on. So now we have convinced ourselves that in the standard model, flavor changing neutral currents can only arise at loop level. Okay, and they are therefore suppressed, right? However, what I'm now going to show you is that even at loop level, there is additional suppression. Okay, so if you're a loop, it's going to be suppressed by 1/16 pi squared. That's a given. But what I'm now going to show you is that the suppression is even more than that. Okay, and that's because of the Jim mechanism and because of the form of the Secant matrix. So consider this process, B to S gamma. Okay, so this proceeds through what are called penguin diagrams. Okay, so the B splits up into an up-type quark. Okay, so UC or T, and the W, and then you close the loop and spit off a gamma. And the gamma can also come out of the W. Okay. So these are penguin diagrams. Right? And these diagrams are the leading source of B to S gamma in the standard model. Okay. And this is a flavor changing process, and the B and it's neutral. because the B and the S, okay, have the same charge. So now here's the thing. If we neglect the masses of the up-type quarks in the loop, okay, so let's say you set the mass of the up-type quarks to 0, right? Then the loop amplitude is the same for all the, you set the masses to 0. That's the only thing that distinguishes these particles. And so the amplitude is proportional to this combination, this product of CKMs, okay, which vanishes because the CKM is a unitary matrix. Okay. So what that means is if these quarks all had the same mass. Okay, sorry, if these quarks were massless, right, this amplitude would vanish. Okay. Now, if you spend some, so this amplitude is only non-vanishing to the extent that the quark masses are non-vanishing. Okay, the mass of the quarks in the loop have to be non-vanishing for this thing to be non-zero. Now, so you calculate this thing. The amplitude scales like the product of CKMs times some function which depends on the masses. Okay? If you set the masses to 0, you get 0. Now, if you spend some time looking at this loop, what you'll find is that the amplitude has support when the loop momenta are of order the W mass. So this function has the property that it scales like mi squared over mw squared, and the quark masses are small compared to the W mass, and it's order 1 when the quark masses are large compared to the W mass. Okay. And this constant is order 1, right? Okay, so already you can see that for the light quarks, this matrix element is going to be very small because it's suppressed by the square of the masses of the light quarks over the W mass, right? So at this point, let's spend a minute and think back about the flavor structure of the CKM. So this is the CKM, okay? And it has this kind of a structure. All the diagonal elements are 1, and the off-diagonal elements are all small. Okay? So these are about the Cabibbo angle, 0.2, and these are even smaller. So then let's look at the contribution to this amplitude from the charm quark. Okay. So that scales like this product of CKMs, which is pretty small because lambda is 0.2, and so this is 0.04. And it's very suppressed because of MC over MW is 1 over 80 or something, right? It's squared. Okay. So you have this suppression by the ratio of the quark mass over the W mass squared. This is called the GIM suppression. Okay. GIM are the initials of the people who noticed this suppression. And you also have this suppression because of the mixing because of the CKM mixing angles. Okay? So it's very suppressed, right? And if you look at the contribution from the charm quark, you would get M up here, and so this would be even smaller, right? For the top quark, this is not a suppression anymore because the top is much bigger is heavier than the W. And so this function actually becomes an order 1 constant. Okay? So there's no suppression there. But you do still have a CKM suppression because all the mixing angles of the top are small. They all begin at order lambda squared. Okay? They have to be either lambda squared or lambda cubed. So you can see that this process is not just a loop suppression. Okay, the contribution is dominated by, in this particular case, by the top quark, and it's got an additional suppression of about 0.04 or something. Okay, right. So the point I want to make is these features are general. Okay, there's nothing. I picked a simple example, but this is a general feature of the standard model. All contributions to FCNCs, okay, are Jim suppressed. Okay, they have this suppression over the light quark mass of the W, unless they involve the top quark. Okay, the top quark is special because it's the heaviest. Okay, it's heavier than the W. So in that case, you don't get this Jim suppression. Okay, but the point is the mixing angles of the top quark are all small. Okay, so there's always going to be additional CKM suppression in the case of the top. And if you're looking at some process in which the external quarks are like first generation, okay, light quarks, that mixing angle suppression is often so large that it's even bigger than the Jim suppression. And so the bottom line, flavor changing neutral currents in the standard model are very suppressed. At tree level, they're completely absent. At loop level, they are present, but they're suppressed by a combination of the Jim mechanism and CKM mixing angles in such a way that that it's parametrically even much smaller than one loop most of the time. Okay. So let me stop here and ask if there are any questions.
Okay. So I think you already answered to Sudipta because she asked why the flavor changing neutral current suppressed in standard model before we started her explanation. So Sudipta, if that's not clear, ask again. And then Miguel, yes, she said that it's clear. And Miguel Bula, he's asking if are the discrete symmetries an example of these additional structures that are required to avoid flavor changing neutral currents?
Pardon, I didn't hear that.
If the discrete symmetries are an example of additional structures that are required to avoid flavor changing neutral currents.
Yeah, they could be. It depends on exactly how you implement it, yes, but it could be.
And Tessio Mello is asking, why is the amplitude proportional to the mass of the quark squared divided by MW squared?
Okay, so let's look at it. Okay, so sure, that's a good question. Okay, so you need at least one part of the quark mass here, okay, because of the chirality. Okay, so this is a dipole moment operator. Okay? So you so it's B bar sigma mu nu S F mu nu. Okay, and so you're coupling so this is B left S right. Okay, in chiral space. Okay, and for B left to S right, to get the chirality to work, you won't get it to work unless there's a mass in here. Okay. But that explains why there's one part of the mass. I'm not sure why it should be squared. That's a good question. I'll have to think about that.
Okay. Yeah, Tessio has a follow-up. He's saying that, well, Sanket Doshi is asking whether this is the fermion propagator. And
Pardon, this is a what?
The fermion propagator.
Yes, it is, of course, coming from the fermion propagator. It is, of course, coming from the fermion propagator. Yeah, but the claim is, the fermion propagator also has a p/p piece as well, and the claim is that that piece is not contributing because the chirality structure doesn't work. That's the claim, and
right.
To get the chirality structure to work, you need a chirality flip here. I need to think about it. That's a good question. But so you need one part of the mass. I'm not clear to me off the top of my head why this is squared. Okay.
Oh, the W mass square is the propagator.
No, that again is a little bit tricky because the loop momenta are of order the W mass. So one can't immediately say, suppose it was a tree level process, that would have been right. But because it's a loop process and the D4K, the loop momenta is going to be of order the W mass. So it's going to be whatever is suppressing the loop divided by the appropriate power of the W mass. And that's why I'm not, that's why it's a little bit tricky.
Okay, so probably you answer this in the Q&A tomorrow. Okay. There are more questions about this, so yeah, so people just wait until tomorrow, please. And then there's a question from Sudipta asking if Vev-less scalar can contribute to flavor tangent neutral currents.
Oh, yes. Yes.
Actually, maybe I see two hands up. So Sudipta, please go ahead.
Hello.
Hello.
Yes, sir. So I am talking about this penguin diagram. So in the penguin diagram, that external photon is also going out. So when we write the matrix element, then we have to write the propagator fermion propagator 2 times. So 2 times we will get q slash plus m and q slash plus m, and also 3 gamma. Also different chiral contribution will also be there. So maybe those q slash term will not contribute, only mq square will come.
Yeah, that's possible. The whole point is to understand why, right?
So yeah, I think we should postpone these questions for tomorrow. There's also Christian Murtsev. He put up a reference for the original penguin calculations of Inami Lin, and the answer may be there. But let's postpone discussions about this ratio for tomorrow. Okay. Okay.
Okay, sir. Thank you.
Sorry.
Okay, sir. Thank you.
Okay. So let's wait until tomorrow. Okay, Chacko, please go ahead.
No more questions. All right. So, all right. All right. So let's come to the last feature of the standard model I want to discuss, which is custodial SU2 symmetry. Okay, so what is this? So point is this: in the limit that the hypercharged gauge interactions and the Yukawa couplings are turned off, the Higgs sector of the standard model has an enhanced symmetry. Okay. So to see this, let's consider the potential for the Higgs. So, so this is the the usual Mexican hat, right? And let's write this out explicitly in terms of real fields. So so the Higgs is a complex, right? It's complex, expanded out in terms of real fields, like this. And then what you see is that mod h squared is looks like this. And so V of h depends on h only through this particular combination, right? And you just look at it, and it's obvious that this has an O4 symmetry, okay, or an O4 rotational symmetry, in which you can rotate any of the h's into each other. Okay, so in other words, even though this potential we wrote, right, is the most general renormalizable thing that's consistent with SU2 cross U1. Okay. If you actually expand it out, it has a much bigger symmetry than SU2 cross U1. SU2 cross U1 has only 4 generators. But this potential, okay, which was the most general allowed by the symmetries, actually has an O4 symmetry. So it has 6 generators, not the 4 of SU2 cross U1. Okay. So the Higgs potential has a bigger symmetry than the Higgs potential has a bigger symmetry than just SU2 cross U1. Now, when the Higgs gets a wave, right? So let's say the wave is sitting along each knot. Okay. Then you can see there's still a residual SO3 symmetry among these 3 guys. Okay. So the SO4 symmetry, the Higgs gets a wave, the SO4 symmetry is broken to SO3. Okay. So normally when we say when the Higgs gets a wave, the SU2 cross U1 is broken to U1, right? And that's of course true, but what we are actually seeing is that if you're only talking about the Higgs potential, right, the unbroken symmetry is also bigger than U1, okay? It's actually SO3, right? So before symmetry breaking, the Higgs potential has a bigger symmetry, which is SO4. And after symmetry breaking, it still has a bigger symmetry, which is SO3. Okay. So the bottom line is the Higgs potential has a bigger symmetry than SU2 cross U1. And even after electroweak symmetry breaking, some part of this bigger symmetry survives, okay, as SO3. So up to now, we have only been talking about the Higgs potential. Okay? We haven't turned on any of the gauge couplings or Yukawa couplings or anything. Okay? Now, there's a very interesting fact, which is that the SU2L gauge interactions also respect this bigger global symmetry. Okay. So to see this, recall that the Lie algebra of SO4, okay, remember the Higgs potential had an SO4 symmetry. The Lie algebra of SO4 is the same as that of SU2 cross SU2. Okay. And it's this extra, so one of these SU2s is the SU2 left of the standard model. It's the second SU2 that I'm interested in, okay, which is an additional symmetry of the Higgs sector, and I'm going to show you that it's an additional symmetry even when you turn on the SU2 left gauge interactions. Okay, so what I'm going to do is to write the Higgs potential in a way that makes it clear that it's invariant under this product of SU2s. This first SU2 is SU2 left, but there's this additional SU2, right? And this additional SU2 is what we're going to see later is related to what's called custodial symmetry. So consider the Higgs doublet, right? Now, we can construct this object I sigma 2 H star, which looks like this. And this is also a doublet of SU2, okay, which you can verify for yourselves. But it has the opposite hypercharge because this is H star. So then we can write covariant derivatives for the Higgs. And the covariant derivative acting on H star because H star has a different has the opposite hypercharge, it has to have a plus here. Okay, that's it. So this is the definition of the covariant derivative acting on this. Now it's convenient to define this bidoublet field, which is made up of the Higgs and this object, and to what we can do is we can write the Higgs Lagrangian in terms of this bidoublet field. So for example, the trace of the phi dagger phi, the trace of this bidoublet is the mod H squared. And so we can write the entire potential for the Higgs in terms of the bidoublet. And we can also write the gauge covariant kinetic term for the Higgs in terms of the bidoublet. But we have to define the gauge covariant term carefully. So it looks just like the usual gauge kinetic term, but because the phi contains I sigma 2 H star, okay? And so because of hypercharge, we have to put in this extra sigma 3 at the end. Okay? So that accommodates the fact that H and I sigma 2 H star have different hypercharges. Right? But once you do that, okay, so there's some algebra which will convince you that then this works. Okay, so there's some algebra which I've done explicitly, but verified that trace du phi dagger du phi gives you back du h dagger du h. I know I'm going rather quickly, but it's all worked out very explicitly in my notes. In your own time, do take the trouble to verify that it all works out. So this Lagrangian is invariant under SU2 left and U1 hypercharge. Okay, so under SU2 left, phi goes to L phi, d mu phi goes to L d mu phi, and you can verify that the trace of phi dagger phi and the trace of the gauge covariant kinetic term are both invariant. And under U1 hypercharge, phi transforms like this, where theta is the angle of rotation. Okay? And this corresponds to, you do a little bit of algebra and you can see that this corresponds to what you usually think of as a hypercharge rotation. All right, so now what I want to show you is that the Higgs Lagrangian has an additional SU2 symmetry in the limit that G prime hypercharge is set to 0. We usually call this symmetry SU2R. Under SU2R, phi transforms in this way. Phi goes to phi R dagger. Right? So trace phi dagger phi is invariant. And when G prime is 0, d mu phi goes to d mu phi r dagger, and this trace is also invariant. So the bottom line is that in the limit that hypercharge is set to 0 and the Yukawa couplings are also turned off, the Higgs sector is invariant under an SU2 left cross SU2R symmetry, under which phi transforms like this. So U1 hypercharge is a subgroup of SU2R. Okay, you can see this from the way we saw the action of U1 hypercharge. Okay. But because the different generators of SU2R don't commute with each other, once you turn on U1 hypercharge, this is not a symmetry anymore. Okay. Now, when the Higgs acquires a wave, phi looks like this. And so both SU2L, which is acting on this side, and SU2R, which is acting on this side, are broken. But there's an unbroken subgroup which corresponds to rotations with L is equal to R. Okay. And so when the Higgs gets a wave, SU2L cross SU2R is broken to broken to the vector subgroup SU2 left plus right. That is when rotations, when R is equal to L, that subgroup is unbroken. This unbroken SU2 L plus R is called custodial SU2 symmetry. Okay. Okay. Some authors call custodial SU2 symmetry this SU2R. Okay, so there's a little bit of a clash in the literature. Most people call the diagonal subgroup custodial SU2. Some people call this SU2R custodial SU2. Okay. Now, the three goldstones are eaten by the Higgs mechanism to give masses to the W and Z. Now, on the SU2L, the W's transform like this. The three W's transform like this. And W is a singlet under SU2R. So what that means is that under the unbroken custodial symmetry, where L is equal to R, okay, the W mu transforms like a triplet. So this is the crucial point. In the limit that G prime, the hypercharge is set to 0, and the Yukawa couplings are set to 0, the W plus minus and the Z must have exactly the same mass. Okay. So any effect that splits the W mass from the Z mass has to be coming either from the fact that hypercharge is non-zero or because the Yukawa couplings are non-zero. Okay? And this is true to all loop orders. Okay, this is because, you know, it has to be coming from an effect which is breaking custodial SU2, right? And the only effects that break custodial SU2 in the standard model are associated with hypercharge and with the Yukawa couplings, especially at the top, because that's the only big Yukawa coupling in the standard model. Okay? So if you go beyond the standard model, very often there's going to be some effect which is not related to hypercharge or the top, which is a new source of breaking of custodial SU2 and splits the W mass from the Z mass. And that's very constrained. Okay, that's the point I'm trying to drive at. Okay? There's a limit in which the standard model has this additional symmetry. The effects that break it are pretty small because hypercharge is small, and the top Yukawa only feeds in at loop. Okay, so if you have any additional source of SU2 breaking from new physics beyond the standard model, it's going to be powerfully constrained by our measurements of the W mass and the Z mass, for example. Okay, so let me end here and ask if there are any questions.
Hey, Chacko. So are there any questions for Chacko? No, it has been a long day. We had 4 lectures today instead of 3, usual 3. Sorry about that. So you can either write or raise your hand, and I will transmit this to Chacko. Okay, I don't see any questions, Chacko. Ah, yes. So just compliments your lectures.
It's nice.
Okay, so okay, so tomorrow we have the usual Q&A session. So if you have questions, you can ask in the Q&A.
Oh, by the way, I should probably say there's this one homework problem that you probably know enough to do now.
Yes, so the homework is embedded in the lecture. Okay, good.
Okay. So,
okay. No, wait, there's a question here from Andres Barreño. He's asking you if you can explain again why the breaking of custodial symmetry causes the difference between the masses of the bosons.
Okay, so I went over that a little bit quickly. So the SU2 left, okay, the SU2 left respects the custodial, fully respects SU2L cross SU2R. Okay. So the Higgs potential respects SU2L cross SU2R. Okay, basically that's SO4. Okay, so that's pretty obvious. But what's not so obvious is that the SU2 left, okay, the SU2 left weak interactions are also invariant under SU2 left cross SU2R. Okay, fully invariant. Okay, now when you turn off the hypercharge and the top Yukawa and the Yukawa couplings, then what you're left with is a theory that is completely invariant under this SU2L cross SU2R symmetry. Everything is invariant, okay, under this symmetry. Okay. Then when the Higgs gets a Vev, this symmetry is broken to this diagonal SU2, which is the custodial SU2. Right. So this is how the W bosons used to transform. Okay, when you had both SU2 left and SU2 right. Okay, but the question is, how do they transform under this residual symmetry, the custodial symmetry? And they basically transform the same way. They transform like a triplet. They transform like this. Because the only thing this is telling you is that the only symmetries that are allowed are those in which L is equal to R. So you do this transformation and you rotate R at the same time, but that doesn't do anything to the W's. And so what this symmetry is doing is it's mixing up the W's. Okay, and this is an unbroken symmetry. It's mixing up W1, W2, W3. And that the only way that can be a symmetry is if the three W's have exactly the same mass. Okay, so that means that the W plus, minus, and W3, okay, and in this limit, W3 is the Z, because hypercharge is 0. Okay, so in this limit, W plus, minus, and W3 will have exactly the same mass. Okay, so any splitting between the W plus, minus, and the Z has to be coming from the fact that hypercharge is non-zero and that the Yukawa couplings are non-zero.
Right. So I think Sudipta has the same question. So in the limit of G prime going to 0, W1, W2, W3 are rotational invariant. Is this the exact custodial symmetry?
I don't quite understand the question. What do you mean rotationally invariant?
I guess you can just rotate
that's
them.
Right. That's right. You can rotate them into each other under this transformation. Oh, by the way, I should ask, can you see my pointer?
Yes. Yes.
Okay. So yeah, that's right. So this transformation rotates the W plus, minus, and W3 into each other.
Yeah.
And the point is that if the custodial symmetry is in the limit of exact custodial symmetry, that's still a symmetry, and that means their masses are the same. That's correct. Yes.
Alison Silva is asking, can the symmetries of the potential before the Higgs acquire a BEV be thought of as symmetries of the Poincare group?
No, this is in an internal space. This is in an internal space. You're rotating the particles into each other, but you're not changing X, Y, Z, or T.
Okay, so I don't see any other questions or hands. So Chacko, thank you very much for this first lecture. Thank you all for attending, and we'll see you all tomorrow morning, okay? Morning, Brazil. Thank you, Chacko. Thank you all.